All right, welcome to the very first video in my entire history doing this channel on calculus. And generally when we start calculus, we obviously start with univariable calculus where we're just dealing with one variable. And before we ever get into the heavy-duty things like derivatives and antiderivatives and so forth, we always talk about limits. All right, what we're going to do in this video is I'm just going to show you basically why limits are important. Okay, you probably have mentioned limits in your class so far, but we're going to go over what is a limit. And the most important thing we need to do is talk about why limits are necessary. All right, so most people probably have to take calculus. It's a pain in the butt. Nobody likes calculus. But in reality, calculus is really, really important, especially when you're calculating things that if you try to do it algebraically, they're actually impossible. Okay. And to illustrate this, we're eventually going to do a very simple limit calculation using this equation right here. This is actually something that was determined by Isaac Newton, or Sir Isaac Newton. This is the equation if you want to find out the force of gravity between two species or two objects, M1 and M2, the gravity between them, all right? And we're going to come back to that in a minute. But to do this, we have to answer three questions, all right? Number one, what is infinity? All right. We've often heard of things that are infinite, or we've potentially heard the universe's volume is infinite, but what is infinity? And I think a lot of people, when they hear this term, although the universe is infinite or whatever, maybe it's not, but I mean, you hear that all the time, you tend to think of infinite as a number. And even probably in high school and probably when you were first introduced to this concept, it sounded like it was a number. In fact, infinity is not a number. It's actually a direction. And that includes positive infinity and minus infinity, or negative infinity. It's actually a direction. So what does it mean that it's a direction? Well, it's useful for if you wanted to see how a function behaves. So let's say you have a function modeling some physical process. If you want to see how that function behaves, if you just let it go indefinitely, well, you can't measure something if it's going indefinitely. But if you want to see how something behaves, if the number gets really, 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 really high, or if it's negative, really, really, really low, then all infinity does is it helps you determine the behavior of a function as what we usually say the independent variable gets very large or very small. Okay? So we'll look at an example of how that's useful in just a minute. But all infinity is, it's not a number, it's a direction. It specifies or talks about the behavior of some function as the independent variable gets very, very large or small, okay, depending on if it's positive or negative infinity. And an example would be, if I had the function, if I had f, the function is equal to let's say I had the function 3x. So the function is 3x. Well, how does this function f behave as x gets larger and larger and larger? Well, the way you can sort of think about it, even though it's not technically and rigorously correct to do this, is you could essentially, if you wanted to see how f behaves as the function approaches infinity, I could just say, plug an infinity into here, and the function is therefore going to tend towards infinity, meaning as x gets larger and larger and larger, the function itself, f, gets larger and larger and larger. Okay? So infinity is not a number. This is just saying as if I were to let x go indefinitely in one direction, then this is the tendency of what the function is going to do. Okay, so that's all it's useful for. And one thing that's technically rigorously true is you can't just plug infinity in for things because it's not a number. And so if you want to specify where a function is going based on where the independent variable like x is going, you have to use something referred to as a limit. So the way to think of a limit is it's useful for things that you can't directly measure. Give you a perfect example. From your algebra days, you probably heard that you can't do this. Let's take a number 4 and divide by 0. Okay, what's wrong with this picture? Well, you have a 0 in the denominator. That's definitely not right, according to what you learned in probably high school algebra or college algebra. Okay, you can't do this. However, what this is essentially saying is that what's happening to this fraction as the denominator gets smaller and smaller and smaller and smaller. I mean, here's a great example. I can't divide by 0, but could I divide by 0.1? Yeah, I could do that. Could I take 4 and divide by 0.01? Yeah, I could do that. Could I take 4 and divide by 0.001? Yeah, I can do that. I can basically take this 4 and divide by an increasingly smaller number, okay, to where I could eventually have 4 divided by 0.00000, an infinite number of zeros, 1, okay? And so what's happening to this function, 4 over whatever number this is, as I approach 0? Notice, if I'm approaching 0, this denominator is not equal to 0, it's just tending towards 0. All right? So what is a limit? Well, this is typically the nomenclature you use for a limit. You say the limit as x goes to usually some number, n, the limit as x goes to n for some function has to equal something else. Okay, so if I wanted to express this, like 4 over whatever number, I could just say, well, this could be, I could have a function y is equal to 4 over x. Okay, and for x, I can't just plug in 0, but maybe I'd like to see how y behaves as x gets very, 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 very close to 0. Okay, but not hitting 0. So what I can do is I can essentially say the limit as x approaches 0. Notice, I didn't say x equals 0. And when I want to use the term approaches, I use this arrow from the variable to the number that the variable is approaching. The limit as x goes to 0 of y, and what's y equal to? Well, I have the limit as x approaches 0, y is equal to 4 over x, and I want to see where this function is going towards. Okay, and it turns out that this function, if I divide by an increasingly small number, meaning it's getting smaller and smaller and smaller, you would find that this function approaches infinity, meaning it just gets larger and larger and larger and larger and larger and larger. I can't just take 4 divided by 0, I can't do that. But I can say the limit of 4 over x as x approaches 0 goes to infinity, all right? Meaning it's getting larger and larger and larger. This is the direction it's going, okay? And that's what limits are useful for, okay? Because you can't divide by 0 and you can't plug in infinity like it's some number, okay? That's not legal. The third question I want to ask is, what is calculus? All right, that should be an exclamation mark. What is, or a question mark, what is calculus? Well, you've probably heard of integrals or antiderivatives and then derivatives and so forth, but it's a lot more subtle than that. In fact, my Calculus 2 professor in college, the very first day of class, we really didn't do much in terms of calculus, but he posed us a question. He says, what is the difference between calculus and everything algebraic that you've done before? And the answer is limits, okay? We're going to find, and we're not doing this anywhere near yet, but a derivative, and this is a derivative right here in case you haven't seen it, this is actually defined by a set of limits. And this is an integral right here. This is defined by a set or at least one limit, okay? So the thing is without limits, you can't do calculus. That's why you start with limits. And it's important to be able to understand what a limit is, okay? And essentially what a limit is, it's if I wanted to say, how does this function 4 over x behave when x gets really, really, really close to 0? Well, I'm essentially saying that there's some distance between 0 and x, but it's so infinitesimally small that I can more or less say x is 0, but it's not 0, it's approaching it. It's so close to 0, but not quite 0. okay? And what we usually say is that there's a differential difference between 0 and whatever x is. It's so close, but not quite. And that's essentially what we're talking about when we're dealing with limits. And one of the things that's really useful about limits is whenever we have something where we have to evaluate a function at infinity, or we need to evaluate something where something like in the denominator is 0, this is when we essentially have to use limits. All right, and I'm going to show you kind of a physical example and then a chemical example of how this is useful, just so you're not thinking you're just doing this for the sake of doing calculus. All right, so here I have the general equation for the force of gravity between two species, where the force of gravity is equal to some constant g, this is a determined constant, times the mass of object 1 times the mass of object 2 divided by r squared, or the square of the distance between the two objects. Now, if I were to determine this for, say, two planets, okay, planet 1 and planet 2, then the equation becomes g, the constant, times the mass of planet 1 times the mass of planet 2 divided by the square of the distance between them. Now, essentially, g is a constant, and because the mass of the planet really doesn't change, all this stuff up here is just a constant. So you could sort of think about this, if the force was y and r was x, this is sort of just like y is equal to some number over x squared, right? This is a function that you've probably seen before, something like this. So what I'm going to do is I'm going to solve this just to show you what happens, but I'm going to do it in sort of notation like this. All right? Now the question is, I want to know what's the force of gravity between these two planets if they are an infinite distance apart, meaning they are so far apart that if the universe was infinite or whatever, they're at opposite ends. I mean, they're so far apart. Now, obviously, infinity is not a number, right? You can't say they're an infinite distance apart. What I want to do is I want to look at the tendency of the force of gravity when they're just so far apart that they really can't feel each other. All right? So let's see what that is. So what I'm going to do is I'm going to take the limit as x goes to infinity because the distance is so great. What's going to happen to the force of gravity, okay, when I do this, all right? So what's the limit of x goes to infinity of 7 over x squared? Well, one way to think about it is anytime you have some number, could be anything, and you're dividing by infinity, or infinity squared, or whatever. That's just 0. Okay, that's something we'll learn. So whenever you have the limit of x goes to infinity of something like 7 over x or 7 over x squared, 7 over x cubed, this limit is just 0. And I could even write that in terms of this equation over here. Let's say the limit as r goes to infinity of g times the mass of planet 1 times the mass of planet 2 over r squared. It's the same thing. This stuff up here, we just said was a constant. Oops, that was not supposed to happen. This stuff over here, up here in the numerator, is a constant. So what happens when I take the limit as the radius, or the distance between the two planets, goes to infinity? Again, it's just 0. So when two planets are a humongous distance apart, the gravitational force they have on each other is basically 0. Okay, or we would say it's negligible because you can never get an infinite distance apart. Okay, so what I just showed is the tendency of the force of gravity as two bodies get just an unrealistic distance apart. Okay, again, I can't say they are an infinite distance apart because infinite or infinity is not a number. But I just said, what is the tendency of this function, gravity, as the distance goes off to a huge number, something we can't even fathom. And basically, we say that the force of gravity tends toward 0. Okay? And that's one thing that a limit is useful for. Here's another example. I'm going to do something a little bit different here. All right? Suppose now, ultimately what I wanted to do is, suppose I wanted to look at the potential energy, V, the potential energy between two charges, charge 1 and charge 2. And by the way, K is a constant. Q is the symbol for charge in this case, so this is a constant K, turns out to be Coulomb's constant, times the charge 1 times the charge 2 divided by the radius, or the distance between these two objects, or these two charges. So the example I'd like to use is, what if, for example, if I have one proton, here's a proton. Protons are in the nucleus. They have a charge of about 1.602 times 10 to the minus 19th coulombs. And let's say I have a second proton, right? Let's suppose I were to move this proton. I fix this one in position. This one's fixed. But I move this proton so close to this proton that it's essentially right on top of it. Like they're essentially, I mean, this proton is exactly where this proton is. I mean, the distance is 0. They're right on top of each other. Now, in reality, I can never get this proton right on top of this one over here on the left. I can never do that. Okay? It'll never happen. I can never get them to where the distance between them is 0. But I can certainly approach 0. Okay? I can get them very, 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 very close to each other. And I just want to see what's the tendency of the potential energy when the distance between these protons becomes vanishingly small. Okay? So again, I sort of have this potential energy equals K Q1 times Q2 over R. But again, these things are just constants right here. So I'm just going to say that's like 3. And then this R in the denominator is sort of like X. So let's look at it. What's the limit as X goes to what? What is X tending towards? Well, we're trying to see what happens to the potential energy when the distance becomes vanishingly small, when they're basically right on top of each other, which they can never be, but we're going to try to get them infinitely or infinitesimally close together. Okay? So X goes to 0 of 3 over X. Well, what's going to happen is this limit is going to tend towards infinity. Okay? Meaning what's going to happen is as the distance gets very, 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 very small, the potential energy is just going to blow up really fast. And one way that you can actually denote a relationship like this is you can say, as R decreases, you can say that the potential energy increases. This is actually one thing we often do in physics and chemistry and so forth. But if I want to do it in terms of this right here, the actual equation for potential energy, what's the limit as R goes to 0 of the potential energy between charges 1 and 2? Well, this is the limit as R goes to 0, meaning the distance is becoming vanishingly small, for K times Q1 times Q2 over R. And again, we're just treating all this stuff up here like a constant. So what's happening to the potential energy? So the limit as R goes to 0 of the potential energy is what? It's tending towards infinity. And again, it can't equal infinity. In fact, if you ever get something where you have a limit that tends towards infinity, you either say it tends towards infinity, it doesn't equal infinity, it tends toward it, or you can just say it does not exist. And in general, in calculus, you usually just say this, it does not exist. D&E does not exist. But sometimes in physics and chemistry lingo, we actually say it just tends towards infinity, and the way that we denote that is just by using this arrow notation. It doesn't equal infinity, but it tends toward it. Okay? So that is basically the purpose of limits. It's for when you have things where you're evaluating a function as it tends towards infinity, or when you're dividing by 0. Okay, you can't do that. And in some cases, we would like to theoretically divide by 0, as in the case of a derivative, and we'll talk about that much later. But we don't want to divide by 0, but we want to divide by something that approaches 0. And that's what a limit is for. Okay? So I hope this video gave you a little bit of intuition on what a limit is, what it's used for. Please make sure to like this video and subscribe to the channel for future videos and notifications. Thank you very much. And in the next few videos, we're actually go over techniques for solving various types of limit problems. Thank you.